Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the mode choice. The mode choice stage is the third step in the traditional four-step transportation demand model. This stage involves calibrating models that mathematically describe travelers' mode choice behavior and using these predictive models to analyze and predict modal shares. In the first stage, trip generation, the trip productions and trip attractions for each traffic analysis zone are predicted. Then, in the second stage, trip distribution, a PA matrix is constructed. The mode choice phase takes this matrix as input data to calculate travel volumes for each transportation mode. Before conducting the mode choice analysis, the analyst must make an important technical decision regarding the treatment of the PA matrix. Specifically, they must decide whether to perform the mode choice analysis directly on the non-directional PA matrix or to first convert the PA matrix into a directional origin-destination matrix and then perform the analysis. If we assume a simple binary choice between private automobile and public transit, and further assume that the mode used for the outbound trip is identical to that used for the return trip, it is possible to utilize the PA matrix, which preserves the socioeconomic attributes of the trip production zone. In this case, after the mode choice analysis is completed, the respective PA matrices for automobile and public transit are converted into OD matrices to serve as inputs for the fourth stage, traffic assignment. However, in actual travel environments, the level of service often differs by time of day and direction, resulting in asymmetrical level of service conditions. Congestion levels, transit headways, and travel times may vary significantly between peak and off-peak periods or between inbound and outbound directions. Particularly when multiple modal alternatives such as bus, rail, and taxi are available, mode choice behavior may differ between outbound trips from home and return trips. Even for private automobile travel, travelers such as carpoolers or park and ride users may utilize different modes for each leg of their journey. To capture these complex behavioral patterns, it is reasonable to convert the PA matrix for each trip purpose into an OD matrix prior to the mode choice analysis. This enables more detailed modeling that accounts for multiple transit modes, directional differences, and time of day segmentation. Ultimately, performing the PA to OD conversion prior to the mode choice stage grants analysts the flexibility to selectively utilize either PA or OD data depending on their specific analytical context and objectives. The predicted mode-specific OD matrices then serve as the final inputs for the fourth stage of the modeling process, traffic assignment. The factors influencing an individual traveler's mode choice can be broadly classified into three categories. The first category involves the level of service, or LOS, attributes of each transportation alternative. This includes quantifiable factors such as travel time, travel cost, the number of transfers, and parking availability, as well as qualitative elements such as safety, reliability, convenience, and comfort. Within this category, total travel time can be further divided into in-vehicle travel time, IVTT, and out-of-vehicle travel time, OVTT. This distinction represents a fundamental behavioral characteristic. Out-of-vehicle time, including access time to a station, waiting time, and transfer time, is perceived with significantly higher psychological resistance, often weighted 2 to 3 times more heavily than time spent inside the vehicle, even for the same physical duration. Similarly, travel costs are distinguished between immediate out-of-pocket costs, such as transit fares and highway tolls, paid directly per trip, and indirect costs, such as fuel, insurance, depreciation, and maintenance, which are typically paid periodically. While these indirect costs are difficult to perceive on a single-trip basis, travelers display high sensitivity to immediate out-of-pocket expenses. Therefore, analysts separate these cost types to enhance the model's behavioral realism. Furthermore, although qualitative and latent attributes are inherently challenging to quantify due to subjective perception, they significantly influence mode choice, and continuous efforts are made to incorporate them into discrete choice models. Analysts also investigate whether the functional relationship between these service attributes and travel choice behavior is linear or nonlinear. The second category encompasses the traveler's socioeconomic attributes. These are fundamental factors determining individual accessibility and modal preferences. At the household level, influential factors include household income, vehicle ownership, household size, and residential location. At the individual level, age, gender, occupation, and possession of a driver's license are highly influential. As with service attributes, analysts frequently examine the functional form, linear or nonlinear, of the relationship between these socioeconomic characteristics and mode choice behavior. The third category relates to the characteristics of the trip itself, primarily trip purpose and travel distance. For example, commuting trips tend to prioritize travel time reliability and savings, whereas leisure or non-mandatory trips are more sensitive to cost and comfort. Furthermore, because the perceived resistance to travel time and transit fare structures varies depending on the distance traveled, reflecting these distance-dependent behavioral variations in the model is essential. Ultimately, the central task in the mode choice stage is to determine how to systematically select and combine explanatory variables from these three categories, constructing a model that clearly explains and accurately predicts the complex behavioral mechanisms underlying travelers' mode choice decisions. In the past, diversion curve analysis was used to represent modal split as a curve based on the relative level of service between two modes. However, this approach is limited to a binary choice context, typically private automobile versus public transit, and has inherent limitations in explaining the causal relationships among the various factors influencing mode choice. Consequently, since McFadden, a Nobel Prize laureate in economics, established discrete choice theory in the 1970s, diversion curve analysis has rarely been used in practice. Currently, mode choice analysis primarily relies on probabilistic models grounded in discrete choice theory, namely the Logit model and the probit model. Both models are based on the principle of utility maximization, assuming that travelers choose the alternative that maximizes their own utility. The fundamental distinction between the two models lies in their assumptions regarding the distribution of the random error term, which represents unobserved factors not captured by observed variables in the model. The probit model assumes that the random error terms follow a normal distribution. By allowing for correlations among random error terms across alternatives, it is theoretically superior and highly flexible. However, it has the disadvantage of being computationally intensive and having a highly complex calibration process. This is because its probability expressions take an integral form and do not yield a closed-form solution. In contrast, the Logit model assumes that the random error terms follow a Gumbel distribution and are independent and identically distributed, IID, across alternatives. Based on this assumption, the Logit model has a convenient closed-form expression in exponential form, which enables efficient estimation and forecasting. Although the independence assumption imposes some theoretical limitations, the model's computational efficiency and interpretability have made it the most widely applied model in current practical transportation analysis. To understand the underlying principles of discrete choice models, most notably the Logit and probit models, it is first necessary to examine choice theory and the principle of utility maximization. Ben Akiva categorized human decision-making principles into four primary types. The first is the dominance principle, which posits that an alternative is chosen only if it is superior across every single attribute. The second is the satisficing principle, where an individual selects an alternative that successfully meets all minimum acceptable thresholds. The third is the lexicographic principle, which involves ranking attributes by priority and comparing alternatives sequentially based on this hierarchy. Finally, the fourth is the utility maximization principle, in which multiple attributes are converted into a single composite index known as utility, and the alternative with the highest value is chosen. Discrete choice models are firmly grounded in this utility maximization theory. In this framework, it is assumed that travelers choose the specific transportation mode that maximizes their own utility. Here, utility refers to a standardized numerical value derived by applying weights to various influencing factors, such as travel time and travel cost. Furthermore, these choice models are broadly classified into deterministic and probabilistic models, depending on how total utility is defined. A deterministic model assumes that if the utility of one alternative is even slightly higher than another, every single individual will invariably choose that alternative, resulting in an abrupt all-or-nothing market split. However, actual human decision-making is not so mechanical. Therefore, a more realistic probabilistic model defines total utility, U, as the sum of a systematic measurable utility, V, which the analyst can observe, and a random error term, epsilon, which captures unobserved factors. This sophisticated structure establishes the mathematical foundation for probabilistic discrete choice models. By assuming a specific probability distribution for the random error term, analysts can derive choice probabilities rather than deterministic choices. Under this framework, even when one alternative has a higher systematic utility, the final choice may differ depending on the relative magnitudes of the random error terms. The graph on the left provides a visual example of this probabilistic choice behavior. Although the measurable systematic utility V is higher for alternative J, the final sum of total utilities can be reversed if the realized random error for alternative I, epsilon I, is sufficiently large, or if the error for alternative J, epsilon J, is sufficiently small. This dual possibility of preservation or reversal of utility superiority is the fundamental principle used to mathematically describe the complex and diverse choice behaviors of humans. The graph on the right operationalizes this mechanism through the perspective of utility differences. Assuming that the error variables for alternative I and J follow the same distribution, their random components can be represented as overlapping on a single standardized probability density function curve. In this context, the mathematical condition for choosing alternative I is Ui greater than or equal to Uj, which rearranges to epsilon j less than or equal to Vi minus Vj plus epsilon I. To facilitate an easier understanding of this combined utility probability mechanism, the graph on the right illustrates an example where epsilon I is fixed at an arbitrary point within its continuous range from -infinity to +infinity. In other words, this graph shows the conditional probability when a specific value of epsilon I is given within the context where both error distributions overlap as a single curve. Under this condition where epsilon I is temporarily held fixed, for alternative I to be selected, the random error of alternative J, epsilon j, must be less than or equal to the threshold, Vi minus Vj plus epsilon I. Consequently, as shown in the graph, the conditional probability of choosing alternative I under this specific state is represented by the shaded red area to the left of the threshold.
Although this conceptual example illustrates the conditional probability for a single fixed value of epsilon I, the unconditional choice probability, pi, is obtained by integrating these conditional probabilities over all possible values of epsilon I from -infinity to +infinity. Through this sophisticated probabilistic structure, discrete choice models can mathematically describe the complexity and variability inherent in human decision-making.
The Logit model is a representative probabilistic discrete choice model grounded in the principle of utility maximization. The fundamental expression on the screen shows that the probability of choosing a specific alternative I is equal to the probability that the total utility of alternative I, Vi plus epsilon I, exceeds the total utility of all other available alternatives J. Mathematically, this formulation expands the simple binary choice context shown in the previous graph into a multinomial choice framework. Consequently, the formula initially takes the form of multiple nested integrations over several competing alternatives J. However, much like the previous graphical example, this complex multidimensional integration is ultimately completed by a final integration at the outermost layer, evaluating the random variable of alternative I as it varies continuously from -infinity to +infinity. Unlike the probit model, the Logit model introduces the IID, independent and identically distributed assumption, which dictates that the error terms of each alternative follow a Gumbel distribution and are independent of one another. This specific assumption serves as the key to simplifying an otherwise intractable mathematical derivation. Under the IID assumption of the Logit model, the joint probability density function of the error terms can be expressed simply as the product of independent marginal probabilities. As a result, during the integration process, the cumulative distribution function simplifies into an additive structure, leaving only a single remaining integral with respect to alternative I. In essence, the mathematical derivation displayed on the screen illustrates how a complex multidimensional integral condenses into a single integral with a summation structure, precisely due to this independence assumption. Once this final integration is carried out, the multidimensional integrals are entirely eliminated, yielding the well-known closed-form exponential expression of the Logit model. While practicing analysts do not necessarily need to memorize the theoretical details of such a complex mathematical derivation process, understanding its underlying significance is essential. In other words, no matter how concise the final form of the Logit model may appear, it mathematically incorporates the principles of utility maximization and choice theory with rigorous sophistication. Because the Logit model provides such an analytically convenient closed-form solution, analysts can forecast and evaluate transportation mode choice behavior with high efficiency and speed without subjecting computational systems to the extreme burden of multidimensional numerical integrations. Examining the mathematical structure of the Logit model, the choice probability of a specific mode is expressed as the ratio of its own exponential utility to the sum of the exponential utilities of all available alternatives. In other words, the choice probability reflects the relative share of exponentiated utility that the alternative occupies within the total sum of exponentiated utilities of all available alternatives in the choice set. If we plot the trajectory of choice probability relative to the utility difference Vi minus Vj between two alternatives, it takes the form of a typical S-curve as shown in the graph. The implications of this S-curve are behaviorally significant. In the extreme regions where the utility difference is exceptionally large in absolute terms, meaning one alternative is overwhelmingly superior or inferior, even if the utility difference changes, the resulting change in choice probability is virtually negligible. In contrast, at the point where the utility levels of the two alternatives are similar, that is, in the region where the utility difference is near zero, the choice probability responds with maximum sensitivity to even the slightest change in the utility difference. This demonstrates that the Logit model can reasonably explain the psychological threshold effect and the varying sensitivity to relative utility differences when choosing between transportation modes. The most significant characteristic, and often cited as the primary limitation of the Logit model, is the independence of irrelevant alternatives, or the IIA property. This property originates directly from the IID assumption introduced during the derivation of the model, namely that the random error terms of all alternatives are independent and identically distributed. The IIA property means that the ratio of choice probabilities between any two alternatives remains constant, regardless of the presence or attributes of a third alternative. This can be clearly demonstrated from the Logit formula. When the probability of one alternative is divided by that of another, the common denominator cancels out, leaving only the ratio of their exponential utility functions. Since this equation contains no information regarding a third alternative, the probability ratio between the original two remains unaffected even if a new mode is introduced or its attributes are modified. In other words, if a new alternative enters the choice set and captures existing market share, the Logit model assumes it draws demand from existing alternatives in exact proportion to their original probability shares. While this assumption works well in environments where alternatives are behaviorally independent, it can produce biased or distorted results when alternatives are correlated. A representative illustration of this limitation is the red bus, blue bus paradox proposed by Ben Akiva. Consider a scenario with an automobile and a blue bus that possess equal utility. In this baseline case, each would receive a 50% market share. Now assume that a red bus is introduced which is identical to the blue bus except for its color. Logically, the combined share of the blue and red buses should remain at 50%. However, because the Logit model treats the red bus as an independent third alternative, the model treats this new option with equal weight alongside the automobile and the blue bus. This results in each of the three modes capturing an equal 33.3% share. Consequently, the total bus share is unrealistically overestimated at 66.6%, while the automobile demand is significantly underestimated. This outcome demonstrates how the IIA assumption can lead to systematic distortion when alternatives share unobserved attributes. For this reason, when applying the Logit model in practice, it is essential to verify whether the random error terms satisfy the IID assumption. If alternatives share many attributes and their random error terms are not independent, analysts should attempt to eliminate the correlation by explicitly including those shared attributes as explanatory variables within the utility function. Another approach is to utilize the nested Logit model, which establishes a hierarchy among modes by grouping alternatives with similar characteristics into higher-level nests.
In mode choice analysis using the Logit model, the most important tasks are specifying the utility function and estimating its coefficients. During this process, the analyst selects explanatory variables that influence choice behavior and determines whether each variable has a linear or nonlinear relationship with utility. Furthermore, a decision must be made regarding the structural configuration of the utility function for the selected variables. The first structural element to determine is the alternative specific constant, or ASC. The ASC serves to capture the unique attributes of each transportation mode that are not explained by observed explanatory variables. An important identification condition is that the number of constants must be no greater than j minus 1, where j is the total number of alternatives. This restriction arises because choice is determined not by the absolute magnitude of utility, but the relative utility differences between alternatives. If a constant is specified for every alternative, a mathematical identification problem arises, leading to an infinite number of possible solutions and making statistical estimation impossible. Therefore, one alternative must be designated as the reference alternative, with its constant fixed to 0, while the constants for the remaining alternatives are statistically estimated. The estimated ASCs for the remaining alternatives are then interpreted as relative preferences compared to the reference alternative. The second specification issue concerns the distinction between generic variables and alternative-specific variables. A generic variable is an explanatory variable that shares a common coefficient across all alternatives. As a typical example, if travel time is specified as a generic variable, it behaviorally implies that a 1-minute reduction in travel time produces the exact same marginal utility increase, regardless of whether the mode is a private automobile or public transit. In contrast, an alternative specific variable allows the same explanatory variable to have different coefficients for different modes. Under this alternative specification, the model recognizes that the exact same variable can have varying behavioral impacts across modes. For instance, a 1-minute reduction in travel time may have a different marginal impact on utility for private automobile users than for public transit users. While alternative specific variables can assign a unique coefficient to every single mode, it is also possible to group similar modes together to share a common coefficient. In summary, the estimation process of the Logit model involves specifying alternative specific constants, determining whether variables enter in linear or nonlinear form, and experimenting with different variable structures. The ultimate objective is to identify the utility function specification that best explains observed travel behavior.
Factors influencing transportation mode choice are categorized into the service levels of each mode, the socioeconomic attributes of the traveler, and the characteristics of the trip itself. Level of service variables typically differ across alternatives. In contrast, traveler attributes and trip characteristics usually take the same value across all alternatives for a given individual. When specifying variables that have identical values across all alternatives, special care is required. In the Logit model, choice probabilities depend on relative utility differences between alternatives rather than absolute utility magnitudes. If a variable such as income is included in all utility functions with the same coefficient, it will cancel out during probability calculation because it appears in both the numerator and denominator. As a result, the variable disappears from the model and has no explanatory power for choice behavior. To address this issue in practice, one alternative is designated as the reference alternative, and its coefficient for the variable is fixed at 0. The variable is then included in the utility functions of at most j-1 alternatives, either as a generic or alternative-specific variable. For example, if an income variable is specified with automobile as the reference alternative, the sign and magnitude of the estimated coefficient indicate both the direction and magnitude of income's effect, that is, whether public transit becomes relatively more or less attractive than the automobile, and by how much, as income increases by 1 unit. This enables analysts to understand how travelers' relative mode preferences change with income from a behavioral perspective. Let's examine specific utility function configurations through the example on the screen. With 3 alternatives, automobile, bus, and rail, the alternative-specific constants, ASCs, are assigned only to bus and rail using the automobile as the reference alternative, thus satisfying the model's identification constraint. For the travel time attribute, the generic specification uses a common coefficient across all 3 modes, whereas the alternative-specific specification estimates a separate coefficient for each mode. This allows the sensitivity to travel time to vary across modes. Similarly, travel cost can be specified as either a generic or an alternative-specific variable. In this alternative-specific example, transit modes, specifically bus and rail, are constrained to share the same coefficient, while the automobile is specified with a distinct independent coefficient to capture its unique sensitivity. For the traveler attribute variable, household income, 2 specifications are illustrated. In the generic type example, bus and rail serve as the reference, and income is included only in the automobile utility function. In the alternative-specific example, automobile is the reference alternative, and bus and rail are each assigned their own income coefficients. Thus, traveler attribute variables must be specified in at most j-1 utility functions, either in a generic or alternative-specific form, to maintain model identification.
In summary, estimating a Logit model requires systematically testing various combinations of variables and structural specifications in order to identify the utility function that most accurately represents real-world mode choice behavior.
A Logit model, which applies the principle of utility maximization probabilistically, expresses traveler satisfaction through a standardized index known as utility. This utility function incorporates various factors influencing mode choice as explanatory variables, and the substitution effects among these variables can be analyzed through their estimated coefficients, which represent the weights of each factor. A prime example of analyzing these substitution effects is the estimation of the value of time, or VOT. The value of time represents the monetary amount a traveler is willing to pay to save 1 unit of travel time. Depending on the analytical objective, analysts can estimate not only a general value of travel time, but also more disaggregated measures, such as in-vehicle travel time, IVTT value, and out-of-vehicle travel time, OVTT value. This enables researchers to quantify the subjective psychological resistance that travelers perceive in various situations into tangible monetary units. The principle of calculating the value of time using the utility function of a Logit model is highly straightforward. It is derived by dividing the coefficient of the travel time variable by the coefficient of the travel cost variable. Mathematically, this ratio represents the marginal rate of substitution between time and cost, specifically the ratio of the marginal utility of time to the marginal utility of cost, where these marginal utilities are the partial derivatives of the utility function with respect to time and cost respectively. Estimated value of time is widely utilized in professional practice, particularly in the economic evaluation of transportation infrastructure projects, where it serves as a key component in benefit estimation. Additionally, analysts routinely verify whether the estimated value of time falls within a reasonable, empirically validated range. If the estimated value deviates substantially from accepted benchmarks, it often signals potential issues in model specification or errors in the underlying data, thereby providing a powerful diagnostic tool for model validation.
In the next lecture of our series on essential concepts and terminology in transportation planning, we will focus on the topic of the Logit model estimation. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.